We're now moving on to the dynamics chapter, which continues looking at motion but concentrates on the forces which are applicable to that motion. I'm going to start off by looking at the different types of forces which you're going to come up against in M1. So, the normal reaction is a force which acts perpendicular to any surface when an object is in contact with that surface. So, for example, when you're stood on the floor, there's a normal reaction pushing up from the floor onto you, and those balanced forces prevent you from falling through the floor. So, for example, on the right-hand example, we've got a ball resting on a surface, so the normal reaction is going to act vertically upwards at 90 degrees to the surface. Whereas on the left, where we've got this slanted surface with the ball on top, the normal force is acting no longer upwards, but still perpendicular to it. The next three forces to look at are friction, tension, and thrust or compression, depending on which name or textbook you might be using. So friction is the force which opposes motion, so that's, for example, a car travelling along a road, there'll be friction between the tyres and the road itself. Tension is caused by things being pulled along, whereas thrust is caused by things being pushed along. So if at any time you think that you're calculating tension but you come out with a negative value, it will be because you're actually considering thrust or compression. And the last type of force we're going to look at to start off with is gravity. So it should be a well-known force already, and gravity causes weight. So the first thing that you need to know about gravity is that weight is calculated by taking the mass of the object and timesing it by acceleration due to gravity, which we know from SUVAT to be 9.8. When we draw that on a diagram, it's normal, so for example for this ball here, which has got an unknown mass, we will draw a vertical arrow downwards, and as weight is calculated by doing mg, I would write mg newtons there. So I'm showing my force on the diagram. On this 4 kilogram area, I would have my downwards force, and I already know the mass is 4 kilograms, so I'd sub that in and I would say that that would be 4g. Now you can see here it's immediately very easy to get confused between 4g, which means a weight of 4g, as opposed to 4 grams. So try and get that into your head now, that when you see 4g on a diagram, that means the weight 4 times acceleration due to gravity. As an example, if we're asked to show the forces acting on a 70 kilogram man as he dives into a pool, here's the 70 kilogram man with very little detail, and downwards would be 70g. Unfortunately, we're probably not just going to be able to deal with one force at a time. There's going to be multiple forces acting on any one object. So what we've got to be able to do is simplify it by resolving the forces in a given direction. And we're normally going to take 2 different directions on any particle. Direction number 1 is the direction in which it's accelerating in. And then direction number 2 is going to be perpendicular to that direction. It's really useful to use colour to help you get these sorted out, as although here we've only got horizontal and vertical forces, soon we're going to start having diagonal forces and everything on a slope. So I'm just going to start off by looking at which direction my acceleration is happening in, which is to the left according to my diagram, and that's horizontal. So I'm just going to highlight all of the horizontal forces which are in play here. So this one just here, and the 80 newtons on that side. Then I'm going to highlight everything which is perpendicular to that, so in this case it's going to be vertical. So now when I resolve my forces, it's going to be really easy to identify which ones I want to deal with. So I'm going to do a little bit in the blue direction, and I'm also going to look at the red direction. Okay, so I'm going to start off by saying which direction I'm resolving in, so that when somebody else is looking at my work, they know exactly what I'm doing. So I'm going to say that I'm resolving, so I'm using my R to say I'm resolving, and I'm starting off by resolving in the direction of acceleration, so I'm going to the left. So I'm resolving in that left direction, and a line, and let's have a look at the forces. So in that direction I've got 80, and then in the opposite direction I've got x. So that's got to be minus the x value. And now we're thinking about F equals ma. So I've resolved all my forces so far. I've dealt with this F part. So now I can set that equal to the mass, which is 4, and the acceleration in the direction that I've chosen, which is 2. So that's my equation so far. Now I'm going to have a look at my vertical direction. So I'm going to resolve perpendicular to it. Now I can either choose up or down here because there's no acceleration either up or down. I'm going to choose up. So upwards I've got y, and then going against the y is a negative 20 and negative 4g. That's all of my forces resolved, so I've dealt with the F again out of F equals ma. So that's equal to the mass of 4 and the acceleration in the direction which I've chosen. There's no vertical acceleration, so that's going to be equal to 0. Okay, so that's how we're always going to start off any problem. We're going to resolve in 2 perpendicular directions and then see how those equations are going to help us answer the question. So we're asked to find the values of the unknown forces x and y. So it looks as if this equation up here, number 1, is going to be useful to help us find out x. So I'm going to take equation 1 and simplify it a bit. 80 minus x is equal to 8. So straight away I can see that x is equal to 72 newtons. In order to find y, I'm going to use equation 2. So simplifying again, y minus 20 minus 4g equals 0. So y is equal to 20 plus 4g, and we know g is 9.8. So that's going to give us y equals 59.2 newtons. Okay, so just to recap the way that I would tackle any of these problems, number 1, I would look for my direction of acceleration and choose a colour to highlight that in. You can pick your favourite colour. Then I'm going to choose a perpendicular direction. I'm going to highlight that in a separate colour. Then I'm going to choose those 2 directions and resolve in them. I'm going to take all the components that are contributing to the force in that direction and set that equal to the mass by the acceleration in that direction, and then do the same for the perpendicular. Then go back to the question and start looking at what am I actually trying to find, which of those 2 equations are going to be useful. Here's a second example. If you're feeling confident, pause the video now and have a go at it by yourself, then come back and check. If not, follow through with me. So we're going to start off by looking at the direction of acceleration, which is downwards. So we're going to look to highlight everything going downwards in the same colour. So I've got mg, I've got 8 newtons, and I've got 10 newtons. And it looks like in this case I haven't actually got anything to deal with in the horizontal, or rather perpendicular to acceleration direction. So that's going to make my life an awful lot easier. Right, so I'm going to start resolving now then. I've finished with my diagram. I'm going to resolve downwards because that's where my acceleration is happening. So downwards I've got mg, and I've also got 8, and against it I've got that 10, so that's going to be negative 10. Remembering that we are using F equals ma. Now that I've got all my forces, that's equal to mass times the acceleration which I'm given, which is 0.5. Okay, so we're going to try and collect all of our terms involving mass onto one side. So I'm going to keep my mg this side. I'm going to bring across that 0.5 m, and I'm going to move across the minus 10 and that plus 8. Okay, so I can factorise now. I'm going to bring out my m as a common factor, g minus 0.5. You could sub in the value of g at this point, but it's good practice to get used to factorising. Okay, that's equal to 2, so mass is equal to 2 over g minus 0.5, giving us a final mass of 0.215 kilograms, correct to 3 significant figures. Still thinking about my presentation and double underlining the answer. in this occasion we're given the problem in words, so we've got to start off in the same way that we did with SUVAT by drawing a diagram. So we know that we've got a particle of mass 5 kilograms, so I'll start off just by drawing a box and labelling it with 5 kilograms. It's on a rough horizontal table and it's pulled by a horizontal force of 20 newtons, so I can mark that 20 newtons horizontally on the diagram. I've chosen for it to be going to the right because we weren't given any further information. Now it's pulling against a frictional force of magnitude 4, so backwards I've got a frictional force of 4 newtons because remember it's opposing the motion, and we're told that given the particle is initially at rest, we've got to find the acceleration of the particle due to these forces, and we can automatically see from the diagram that the 20 is going to beat the 4, so acceleration is happening this way. And we'll look at B and C shortly. So there are a couple of forces which I haven't yet considered. Because I've got a mass, I've definitely got gravity, so I've definitely got a weight of 5g. And upwards, because it's perpendicular to the surface, we've got our normal force. Okay, so I'm going to start highlighting, looking at the direction of acceleration first, which is to the right. So I've got this 20 force across here, and I've got the 4 newtons acting backwards. And then acting perpendicularly to that, I've got the 5g going downwards and the normal force going upwards. So I'm going to come up with 2 equations. I'm going to come up with a blue equation and a red equation. Right, so in the blue, acceleration is going to the right, so I am going to resolve to the right. So I've got 20 minus 4. I know that's equal to, as we're using F equals ma still, as we will do for this whole chapter, mass of 5 and the acceleration in that direction, which is a. Red direction, I'm going to choose upwards. So I've got my normal force acting upwards minus 5g acting downwards, and that's equal to 5 times the acceleration vertically, which is 0. I haven't got my particle flying off the table or falling through the table. Okay, so part A asks us to find the acceleration of the particle. It looks as though the blue equation is going to be handy for that. So if 20 minus 4 is equal to 5a, let's simplify. So that's equation 1. Simplifying equation 1, we've got 16 equals 5a. So a is going to be equal to 3.2 meters per second squared. I'm going to jump to part C now and have a look at the magnitude of the normal reaction. And looking back at our equations, it looks as if equation 2 is going to be pretty handy. Simplifying equation 2, n minus 5g is going to be equal to 0. So my normal force is going to be equal to 49 newtons. Remembering that we can just sub in our value of g, which is 9.8. Now we'll have a look at part B, where we're asked to find the distance travelled in the first 4 seconds. So it looks pretty much as if we've got to suddenly go back and use our SUVAT data which we've had before. So we'll start off by finding out which values we've got. The question asks us to find the distance travelled, so we're going to need to find that. It says that it's initially at rest, so that's going to be 0. We don't know the velocity by the end. We do know that the acceleration is 3.2 because we calculated that in part A, and we're looking for it over the first 4 seconds. So SU, A and T, that's going to be S equals UT plus a half AT squared. S is equal to 0 times 4 plus a half times 3.2 times 4 squared, giving us a final distance of 25.6 meters. Now it does ask for distance and not displacement, but if we look at the acceleration, we know that it's not going to change direction over this course, so we know that in this case displacement is going to be equal to the distance. So just as we're getting used to looking at our horizontal and vertical forces, Here we go, we're going to throw in a diagonal force. So we need to be able to take these diagonal forces and resolve them into the components which are going horizontally and the components which are going vertically. And we're going to do this with the aid of trig, for which we'll need a right angled triangle. So we'll start off by making our right angled triangle. Okay, and we're just going to highlight the two different colours because that's what we are used to so far. Again, in this example, it's not particularly needed, but when there's multiple forces on there, you will find it very useful. Right, so you should be fairly familiar with trig from GCSE, but just in case, we've got our 20 degrees in the bottom left-hand corner, so the red is going to be our opposite, the blue is our adjacent, and h is our hypotenuse, which we're told is 12 newtons. So if we're trying to have a look at the blue bit first, we're going to be dealing with the adjacent and the hypotenuse, so we're going to be using cos. So cos of our angle 20 is going to be equal to the adjacent over 12. So the adjacent, which is what we're actually looking for, is going to be equal to 12 cos 20 newtons. In the red part, we're going to be dealing with the opposite and the hypotenuse, so we're going to use sin this time. Sin 20 equals opposite over 12, so the opposite is equal to 12 sine 20 newtons. If you're going to use these values in future calculations, then I would keep them in their trig form. If not, you can then sub them into your calculator and get out a final value. So the blue component is going to be 11.3 newtons, and the red component is going to be 4.10 newtons. Knowing that this is a right angled triangle, the two components, when squared, should sum to the square of the total. So just to check that quickly now, 11.3 squared plus 4.1 squared, and we're just checking that that's equal to 12 squared. Bearing in mind there's going to be some small rounding errors, that's equal to 144.5, which is very close to 12 squared, so we can assume that we've managed to do these calculations correctly. Here's a more complex example. We've now got three forces to deal with, and we're looking to find the sum of the components in the x and y directions. So we're going to resolve in the x and y directions eventually. So we'll create quite a few right angled triangles, and we'll start off in the same way by highlighting which components are going in which directions. So we've got no acceleration on our diagram, so I'm just going to start off by dealing with x. So I'm going to have a component of the 6 Newton force, and I'm going to have a component of the 5 Newton force acting horizontally. And then acting in the y direction, I've got 10 newtons for sure. Then I've got a 6 Newton vertical component, and I've got a 5 Newton vertical component. I'm going to look vertically first, so I'm going to say that I am resolving vertically, and I'm looking at everything I've highlighted in red. So I've got 10 newtons, then I've got 6, and it's the opposite side to the 40 degrees, so it's 6 sin 40, and then in the negative direction, so going in the negative y direction, I've got 5 sin 45, and we can simplify that to 10.3 newtons. Now looking horizontally, they're both acting in the positive x direction, so I'm going to be adding them together. So I've got 6, and the blue line is on the adjacent to the 40, so it's going to be cos 40, and I've got 5 cos 45. Popping that into our calculator is going to give us 8.13 newtons. I'm rounding each time to 3SF, so it's important that we just quote our accuracy on each answer. Putting these resolving skills into practice, we're now going to have a look at a problem where we've got to find some unknown forces. So before I start highlighting anything, I'm just going to deal with this diagonal 20 newtons force, and I'm just going to make a right angled triangle from it. Okay, and here begins the highlighting. We know that we've got acceleration acting to the right, so I'm going to highlight all of my horizontal forces first. So there's 1, 2, and then we're going to look at the verticals, which are R, which looks like it's going to be the normal force this time, 10G, which is the weight, and the vertical component of that 20 newtons. So I'm going to come up with a red equation, and I'm going to come up with a blue equation. In the blue, I'm resolving in the direction of acceleration, so I'm resolving to the right. So I've got 20 cos 60, because my adjacent side, and the opposite direction I've got F. That's equal to the mass, because we are still using F equals ma. So my mass of 10 times the acceleration in that direction, which is 0.5. That's going to be my equation 1. And then in the red direction, I'm going to choose to resolve upwards. So I've got the force R going upwards. I've also got a component of the 20 Newton force. And downwards I've got 10G. F equals ma, there's my F's. Now I've got mass, which is 10 times the vertical acceleration, which is 0. And that is my equation 2. Okay, so I've got to find the magnitudes of forces R and F. So it looks as though I can use equation 1 to find F and equation 2 to find R. So I'll start off with equation 1. I'll simplify it a bit. So I've got 20 cos 60 minus F equals 5. And I can solve that by rearranging, giving me that F is equal to 5 newtons exactly. Now I'll deal with R, so I'm going to do equation 2, simplify that as best I can. R is equal to, if I move terms across, 10 times 0 is 0, so I've got 10G minus 20 sine 60. We can remember that G is 9.8, substitute that in, and then we'll get that R is equal to 80.7 newtons, rounded to 3 significant figures.